Continuing on physical chemistry, chapter 5, we're beginning section 5 now. Now let's talk about the temperature dependence of reaction heats. So how does the heat of reaction change with temperature? Well, we have the heat of reaction in the standard state, and that's going to be the sum over all the substances I, you can put an I down here, but I guess it's not that important, of nu I, that's the stoichiometric coefficient, times the molar enthalpy of formation in the standard state of substance I. This is at constant pressure, obviously, because it's standard state. Now, the standard enthalpy of formation is known at temperature 1. So we need to find the change in enthalpy in the standard state at temperature 2. So we're going to take the derivative of the heat of reaction in the standard state with respect to temperature. So we have the derivative of the change, or the heat of reaction with respect to temperature. It's going to be the derivative with respect to temperature of the sum of nu I of the molar enthalpy of each substance in the standard state. That's going to be the sum of nu I, the derivative of molar enthalpy with respect to temperature. So now we have the partial derivative of molar, and we know it's at constant pressure, right? So these derivatives become partial derivatives. So we have the partial derivative of the molar enthalpy in the standard state of substance I with respect to temperature holding pressure constant. That's going to be the molar heat capacity of substance I at constant pressure in the standard state. So we have the derivative of the heat of reaction with respect to temperature. It's going to be the sum over the substance I of nu I of the molar heat capacity of the substance in the standard state. And that's just going to be the change in the molar heat capacity at constant pressure in the standard state. So we have the differential of the heat of reaction in the standard state is going to be just the change in the molar heat capacity times the differential of temperature. See how we just multiplied by the differential of temperature. So now we're going to have the integral from temperature 1 to temperature 2 of the differential of the heat of reaction in the standard state. And that's going to be equal to the integral from state 1 to temperature 1 to temperature 2 of the change in the heat capacity, molar heat capacity, with respect to temperature. Now we have the change in the enthalpy at temperature 2 minus the change in the enthalpy in the temperature 1. That's going to be equal to the integral from temperature 1 to temperature 2 of the change in the heat capacity. This probably should be a bigger C there so you can tell. This is like a subscript P actually. But anyway, the change in the heat capacity times dt. This is called Kirchhoff's law. So instead of the integral from T1 to T2 of the change in the heat capacity with respect to temperature, the book has it written like this. They have it written the integral from T1 to T2 of the change in the number of moles times the molar heat capacity at constant pressure in the standard state dt. So basically the book has it split apart with the intensive times delta N. So the change in the enthalpy at temperature 2 in the standard state is just going to be the change in the enthalpy at 298 plus the integral from 298 to whatever other temperature we're interested in times of the change in heat capacity with respect to temperature. Now this value right here, the change in the heat capacity at constant pressure, is available in tables. So let's say we have our reactants at T2 and we want to go to products at T2. So what's the change in the enthalpy of the formation? Well, we have to take the CP, the heat capacity of reactants, times delta T to bring the reactants down to temperature 1. Then we can do the actual enthalpy of the reaction, change in the enthalpy of the reaction. So then we have the products at temperature 1. Then we use the heat capacity for the products times the change in temperature back up to T2. So this is just like before, where we've broken a process down into multiple steps to find out what we need to find out. Now see handout number 20. So we're going to talk about, okay, what if about NO? So we have this change in enthalpy. We want to do 558 kelvins. So that's going to be the change in enthalpy at 298 kelvins plus the change in the heat capacity times the integral from 298 kelvins to 558 kelvins with respect to temperature. We're going to just assume the heat capacity constant pressure is constant. So then we have the change in enthalpy, 558 kelvins, is going to be equal to change in enthalpy, 298 kelvins, plus the change in the heat capacity, times 558 kelvins minus 298 kelvins. So the change in the heat capacity at constant pressure is going to be the heat capacity at constant pressure for the NO gas minus 1/2 times the heat capacity of the N2 gas plus 1/2 times the heat capacity, constant pressure obviously, of the oxygen gas. So that gives us the change in heat capacity at constant pressure. It's going to be 298.86 joules per Kelvin minus 1/2 times 29.12 joules per Kelvin plus 1/2 times 29.36 joules per Kelvin. And that's going to be equal to 0.62 joules per Kelvin. So the change in the enthalpy at 558 kelvins is going to be 90.37 kilojoules plus 6.20 times 10 to the negative 4 kilojoules per Kelvin times 558 Kelvin minus 298 Kelvin. So that just simplifies to 90.53 kilojoules. Let's see handout figure 18, and we'll talk about carbon dioxide. So what's the change in the enthalpy at 298? It's minus 565.968 kilojoules per mole. We want to find it at 1200 kelvins. So the change in the enthalpy at 1200 kelvins is going to be the change in enthalpy at 298 kelvins plus the integral from state 1 or temperature 1 to temperature 2 of the change in the heat capacity dt. You can ignore these scribbles. So the change in the enthalpy at 1200 Kelvin is going to be the change in the enthalpy at 298 Kelvin plus the integral from temperature 1 to temperature 2 of the change in D plus the change in E. What the heck is this? I think that's supposed to be -1. Can't read my own handwriting. Plus the change in F times temperature. Oh no, that was just temperature. Okay, I can't read my own handwriting. That's temperature. Plus the change in F times temperature to the -2 dt. So remember, delta always means products minus reactants, final minus initial. So the change in heat capacity in the standard state is going to be 2 times D plus E times T plus F times T to the -2 for CO2 minus, because that's the product, minus D plus E times T plus F times T to the -2 for oxygen plus 2 times D plus E times T plus F times T to the -2 for the carbon monoxide. So that gives us the change for D is going to be 2 times D of carbon dioxide minus D for oxygen minus 2D for the carbon monoxide. So that gives us 2 times 10.55 calories per mole Kelvin minus 1 times 7.16 calories per mole Kelvin minus 2 times 6.79 times calories per mole Kelvin. And then the change for E is going to be 0.36 calories per mole Kelvin squared. So that's going to be equal to 1.51 times 10 to the -3 kilojoules per mole per Kelvin squared. And then delta F, that's going to be -1448 kilojoules Kelvin per mole. And then we just have to evaluate the three integrals. So the change in enthalpy at 1200 kelvins is going to be minus 565.968 kilojoules per mole plus 0.00151 kilojoules per mole Kelvin times temperature 2, which is 1200 obviously, minus 298.15 kelvins. So that's from the first integral in delta D, plus 5.69 times 10 to the -6 kilojoules per mole Kelvin squared divided by 2 times temperature 2 squared, remember temperature 2 is 1200 kelvins, minus 298.15. I should have shown the units. That's kelvins. Oh no, they pulled the kelvins out here. Well, whatever. They're in there somewhere. So this is from the second integral, delta E. And then minus 1448 kilojoules Kelvin per mole times the quantity of temperature 2 to the negative 1 minus 298.15 to the negative 1 per Kelvin. This Kelvin should be inside. I don't know why they wrote it like that. But anyway, yeah, I'll put it like this. Kelvin squared, Kelvin to the minus 1. Obviously, if you're going to add and subtract, you need the units to match. And this is from the third integral, delta F. So the answer is the change in enthalpy in the standard state at 1200 Kelvin is just minus 557.112 kilojoules per mole. That is the end of section 5.